All right, so let's do another version of a system with two objects in motion connected to each other. Here, over a table or a shelf, we have mass A on top of the table, connected to mass B with a string or a rope over a pulley. That pulley they say to consider massless and frictionless, and what this does, it basically takes out any concerns that the pulley might additionally add to the motion of the system. Later in the year, we're going to add in some complexities where the pulley actually will matter. But for now, let's just say the pulley doesn't really affect anything. The only thing the pulley does is it redirects the force of tension in the string. We need to understand that this string or rope is all the same piece, and so that tension is right now considered to be the same everywhere. And all that pulley is doing is redirecting that tension from up top where it was sideways. Where the tension was sideways, and then after the pulley, now the tension is downward. That's all a pulley does. A pulley just redirects, right now anyway, a pulley just redirects the tension, but doesn't alter the tension within the entirety of the string or the string or the rope or the chain or whatever. And typically, if these blocks are connected, again, we had this discussion before. Those accelerations of each block, it has to be identical, right? And of course, we're assuming constant acceleration, and that means that any instantaneous velocity that these blocks have, they have to have the same exact instantaneous velocity during their motion. They're traveling together. Let's assume there is a little bit of friction between block A and the table or the shelf or the whatever. Block B does not have any friction. It's actually not touching any surfaces. It is in it's hanging. It's not touching any walls or anything else like that. And typically these problems want to know, what's the tension in that string and what's the acceleration of the system. And then other problems will also add in extra stuff after you find the acceleration. And if you know some distances or some heights, or some times, you can find distances or you can find velocities, and you can find all kinds of other wonderful things once you get that acceleration. I'm not going to do that here, but you should be prepared to do that from previous knowledge. So as always, you're going to draw a free body diagram for each object, and I'm going to do the free body diagram for A, and I'm going to do the free body diagram for B. And put in the appropriate forces. We're going to have the tension, which is going to pull A forward. We don't know what that is. We're going to have the normal force of A. We're going to have the gravitation of A. And we are going to have some friction. And we're going to have that kinetic friction. So that's everything acting on A. And again, these problems, we're ignoring the problems that are on angles and all those other wonderful things. There are versions of these problems where, you're on a ramp and the object's on a ramp and there's a pulley and then the pulley goes and the pulley hangs and then there's another mass hanging and is it going this way or is it there's all kinds of wonderful craziness that could happen with these problems, which we're not doing. Okay, we're going to keep everything nice and along the x and the y axes. The free body diagram of B is pretty easy. You have gravity pulling it downward, and it's not in free fall because the tension here is actually preventing it from falling, right? Because that tension is heading back all the way to block A. Now, what I'm not doing here, which I did in previous problems, is I'm not making this all one system. I'm not going to do that here. Now, there is a way to do that. There are some physics teachers and some videos where they're going to say, hey, we can take MA and we can pretend that we can bring MB and we can straighten it and pretend it's being pulled by the gravity of B, and then of course only block A is going to have the friction. There's a way to do that. I'm not going to do that here. I'm not going to do that for several reasons. You can find other videos with teachers explaining that. I don't do it. I have my reasons. I find that it actually causes more confusion and more reliance on tricks than it does on the actual physics. What we're going to do is we're going to pretend that each object is, by itself, and then of course when you do that free body diagram for each of those objects, you only draw the forces acting on each of those objects. So object A only has these forces touching it. Object B only has these forces touching it directly. Yes, it is true that this tension goes back to pull on A and is held back by A because of the inertia of A and the friction of A. And yeah, but that is all true. But block B doesn't know all that. Block B, if I were to personify block B, all it knows is it's immediately being held back by some rope, some tension. And if we accept that, then we can, as always, make formulas for each free body diagram. And once you do that, then it just becomes a math problem. So, in the x direction, we realize that block A is going to accelerate. We're going to say that, that tension, and we are going to make the generalization that positive upward and positive to the right, normal coordinate plane. And we have friction kinetic holding us back, and we're going to say that's going to accelerate mass A. Now it's only going to accelerate mass A. Now what I'm going to do, and you'll see why in a minute, but I'm going to actually backtrack here. I'm going to say mass A, and I'm going to purposefully put in positive acceleration. I'll explain why a little bit more in a minute, but just trust me here, right? Like if this is accelerating, it's accelerating in the if it's accelerating in the positive direction. There's no arguing that right now, not the way we assigned it anyway. And then, we can do what we do. We know force, or we don't know tension. We know that this is equal to mu k times the normal force of A. And then if that positive is there, now I can just keep it ma. And I know m, of course I don't know a, and that's the whole point, right? Like I'm trying to find tension and acceleration, so I don't know two things. Well, if I don't know two things, I need two equations, and that's going to be, again, the theme of this whole kind of this unit, right? Two equations, two unknowns, better solve the equations together. But I'm also kind of stuck here because I don't know the normal force. But we do know the normal force because in these very simple problems, if we know, we know the normal force is going to be equal to the gravitation because you're in equilibrium, and there's no other crazy forces at angles. So force normal A equals gravitation is mag, or for m times g, and then we can plug that in. Now I'm going to be fancy, and I'm not going to plug in the numbers. You can plug in the numbers here. You can plug in the numbers if you'd want, but I'm just going to keep it fancy and no numbers just yet. Now, some students here want to, and I know why, they're going to say, oh, mass is canceled. They don't cancel because there's no mass to divide out of the last term, so you can't say that they divide out, so do not do that. And then we can plug in some numbers if we want, because we're pretty much finalized here. We don't know ft minus, actually, hold on. Let's get my act together here. Minus, how did I say, 0.1. 0.100. Mass A. Now, note, this will move. If you let this go, this will move. Even though mass B is, quote-unquote, lighter than mass A. You know, we went over the concept sheet. As long as that friction is relatively small, it doesn't stop it, make it a static problem. You can have a lighter mass hanging, and it will still possibly move. You don't need a heavier mass I can't talk. You do not need this mass to be the heavier mass to get it to move. That's not necessarily the case. I mean, obviously, if it is the heavier mass, it looks like more likely to move, but this could be the lighter mass, and it will still very easily move, depending upon how much friction you have going on. So keep that in mind. And again, we went over that with the concept sheet. So mass A, we said, was hanging. No, mass A is not the hanging mass. Mass B is the hanging mass. So this is the, oopsie. This is the 20. 9.81 equals 20.0 times A. And you can go and solve this and get a final statement with just some numbers. So let me do that, because I should have done that already, of course. But why would I have done that? 0.1 times 20, which is 2, times 9.81, which is 19.62. So why did I even do that? I don't know. Because it's late, and my mental math is just turned off right now. So we're stuck because we have two unknowns. Well, good thing we have a whole other equation to look at for object B. So summation of the forces for object B in the y equal ma, right? Because we're hanging up and down. And we are going to move downward. And this is important. So our tension is definitely upward when it's positive, minus the gravitation. Now, equals mb. Now watch what I do here. This is probably the most important part of the lesson right here. I'll say that again. This is probably the most important part of the lesson right here. Since we already used that acceleration, because it's an unknown, and we know the accelerations are the same for each object, we're going to use a here. But because we used a, and because it's in a different direction, we must very clearly mark that direction, right? It's a minus direction for this particular object, because if this thing is being pulled, it's accelerating downward. And because we use the same a term, but one is moving one direction in the one scheme and the other is moving the other direction in the other scheme, since the magnitude is the same, we can use the same letter, but the direction in each of our situations is not the same. So we must be very cognizant of that and put the appropriate sign, even if it's an unknown, because we're using that unknown letter in two different set of equations. So you must be careful with the signs of your unknown if you use that letter more than once. And that's going to be the one thing that's going to mess students up. You're accidentally going to plug in an A here.